What up, dudes? We're going to do some physics today, and there's one thing that I wanted to show you guys, and it's about the coordinate system. And it might be funky for you guys at the beginning, but keep this in mind, and I'm pretty much going to dedicate this one lecture to this one concept, and then I'm going to move on to, the next time we meet, I'm going to move on to sine, cosine, and all of that kind of stuff. Actually, maybe I might have time to do that today. Hopefully I do, but if not, I'm fine with that. This one concept has to do with the coordinates, and it trips up a lot of people. So let me show you folks how to do this thing. All right, so say that we're inside of a hot air balloon. And the hot air balloon is going up at a constant speed of 6.5 meters per second. So here's my balloon. Here's me inside of the hot air balloon. And it's going up with a velocity of 6.5 meters per second. We're cool? Can you see that? Or is that too sloppy? That's too sloppy. Okay, here, let's do it. It's going up with a velocity of 6.5 meters per second. So, does that look better? All right, good. Now, the basket of the balloon is 20 meters above the ground, and a bag of sand tied to the thing comes loose. So, at height h equals, I should write it maybe on that side. H equals 20 meters. A basket, a little sandbag comes loose. Got it? How long does it take the sandbag to reach the ground? So, time equals what? That's the question. All right. So, you understand the question that you got a hot air balloon going up at a speed of 6.5 meters per second, and at a height of 20 meters, it releases the sandbag. And I got a question for you. Does the sandbag go up or down immediately? Well, actually, if you're inside of the hot air balloon, you would see the sandbag go only down, right? But if you were on the ground, you would see the sandbag kind of go like this. Does that make sense? Because the velocity of the hot air balloon is 6.5 meters per second up, so the velocity of the bag when it's first released is actually 6.5 meters up. Does that make sense to you? So now what I'm going to do, and this is the part that I think is kind of funky. Actually, I'll tell you what, I'm not going to do the funkiness thing now, but, well, anyway, watch these next few examples and you'll see. One of the things I need to do is put in my acceleration. And I like doing that. Notice how I did my velocities with straight arrows. But with my acceleration, what I like to do is I like to do a squiggly line. And I'm going to put a little G right by it. The squiggly line tells me that's the direction of the acceleration. In this particular case, the velocity is going up, but the gravity is going down. Does that make sense to you? Okay. Now here's the thing that's going to be funky for you. Which direction would you like to call the positive direction? Would you like to call, because we're going to do a coordinate system, right? You want to call up the positive direction. All right. In this particular case, calling up the positive direction actually makes your life a little bit harder. Yeah, I'll give you a second to pick up your brain off the floor. What? In this particular case, down as the positive y direction is the advantage. Would you like to know why? Because there's only one thing that is pointing up. That's this one. But there's two things that is pointing down. One is the gravity, and the other is the height. Does that make sense to you? So in this solution, I'm going to call down, anything pointing down, as the positive direction. Because if you look at it, the vector that talks about the displacement, right? We talked about the displacement. The displacement really cares about where's the final and where's the initial. Well, that vector pointing from the initial to the final is pointing down. Do you see that? So in this problem, I'm going to say anything going down is positive. And what you're going to ask me is, you say, wait, that's confusing. What happens if I don't think to choose down as positive, and what happens if I choose up as positive? And my answer is this. Believe it or not, it's all going to end up being the same thing in the end. There are just two small extra steps you have to take if you call up positive in this particular case. So the coordinate system will work itself out. If you call up positive, if you call down positive. After you do a few of these problems, you'll just have more experience, so that way you can know exactly how to solve these problems. Does that make sense? Maybe I should say you'll have more experience, so you know exactly which approach you want to take to make your life easier. All right. So we've got our five things that we need to list out. It's V naught, V final, delta Y, A, and T. In this case, we know what V naught is. V naught is equal to what? Come on, Kaylin, I'm going to have to pick on you because you're the only one here. 6.5. Actually, it's negative 6.5. Because V naught's going up and we're saying down is positive. Does that make sense? All right. The other thing is acceleration is what? It's positive 9.8 meters per second squared. Most people say negative 9.8 meters per second squared. Yeah, but this time gravity's pointing in the down direction and our positive direction is in the down direction. Our delta y, we know that. Our delta y is positive 20. Okay? And then our time is what we're looking for. So that makes our V final our dkdc. Does that make sense? And if V final is our dkdc, we already know to use that famous equation that Mr. Dalday said you're going to regurgitate so much you're going to be sick of. Delta x equals V naught t plus 1/2 at squared. We cool? Okay. So this is, I don't like plugging in numbers, but in this particular case, I'm going to do it now, so I'll show you folks what's going on. This is positive 20 equals negative 6.5 t plus 1/2. Can I make this, instead of a 9.8, I'm just going to make it a 10. I'm approximating that thing. Is that all right with you? All right. So 1/2 of 10 is just 5. So 5t squared. Are we cool with that? And then to solve this, do you know how to solve for t in this particular problem? Maybe, maybe not. Say I don't know or say yes. Sort of. Okay, I'll tell you what, I'm going to make this thing, I'm going to move things around a little bit and maybe you might recognize it. What about I'm going to move everything over to the left side by subtracting it or adding it to this in the 6.5's case. So that would be negative 5t squared plus 6.5t plus 20 equals 0. What do you see now? Okay, so how do you solve this? Do you know? There's a word, it's an equation, formula, really, that you learned in Algebra 1 or Algebra 2. If you haven't learned it, I can tell it to you. Can you not remember the name? There we go. It's the quadratic equation. Exactly. It's a quadratic equation with this being a t instead of an x. But it's the same form, so you have the same solution. Instead of having x equals negative b plus or minus the square root of b squared minus 4ac all over 2a, you have a t. And your b and a and c are all the same. Careful now, don't get this a confused with that a. This is a for acceleration. This is a for the term that's in front of the square term in the quadratic equation. Do you see the warnings I'm giving you? Okay, let me address this thing real quick before I solve it, and I'm going to plug it into the quadratic equation. But before I do that, I'm going to put a little squiggly line here, and I want to show you something that I think might be interesting. What if we called up positive? What happens if we called up positive? Okay, well that would make v naught equal to positive 6.5, a would be negative 10, delta y would be negative 20, time would still be something we're looking for, and we would still use the same equation because we still don't know or don't care anything about the velocity final. Does that make sense? All right, so I would use delta y equals v naught t plus 1/2 at squared. Notice how I made that switch real quick, and I don't know if you caught this, but the original equation is delta x equals v naught t plus 1/2 at squared. But I changed it to a delta y. I should actually change this to a delta y as well. And we know that because it's simply we're just looking in the y direction instead of the x direction. Okay. Plugging in these numbers, though, you would think that that messes something up. But let me show you something that I think is really cool. I would plug in negative 20 equals 6.5t minus 5t squared. And you're thinking, hey, that looks like that, only the signs are all off. Where you have a positive, you have a negative. Where you have a negative, you have a positive. How is that going to give me the same answer? Well, let me do something like this. Let me take the 20 over to the right-hand side. We cool? I should put probably 0 equals. So I just took that 20 that was over here and added him over to the right-hand side. That's the same equation. You see that? Yeah. The math worked itself out in the end. Basically, what you end up doing is if you called the up direction positive, you end up with two negatives that kind of like fixed, and you end up with like the opposite signs. Well, that's all right. It's just the reason why I like calling down positive in this particular case is because things are generally going down. So I don't have to remember to make this a negative and this a negative. I just have to make that one a negative. Does that make sense? Whereas if I called up positive, I would have had to go positive 6.5. I would remember that. Negative 9.8, I would have totally remembered that. Negative 20, I would have forgotten that. I would have put in positive 20. And that would have changed my answer completely. You see what I'm getting at here? So this idea of being able to choose which direction is positive is completely foreign to students. Every student I know up until this point has always called up positive. But you don't need to. It's an arbitrary choice. You could call down positive. And the math will work itself out in the end, as long as you're careful through the whole problem. All right, anyway, you want me to solve this using the quadratic equation. Here's my A, here's my B, and here's my C. So my answer for T is equal to negative 6.5 plus or minus the square root of 6.5 squared minus 4 times negative 5 times 20, all divided by negative 10. All I did was I plugged this A, B, and C into the quadratic equation. You remember what that is, right? Negative B plus or minus the square root of B squared minus 4AC all over 2A. And you end up getting this. You end up getting negative 1.46 and 2.48, I believe. No, 2.78. So what is your answer? Is it both of these? What is your answer? Because these are the two numbers you get when you evaluate this. It's the positive one. I love that. Exactly. Even though you have a parabola with two answers, the time that we're looking for is 2.78, not the negative 1.46. It's the positive answer. Does that make sense? Because essentially, and here's what's going on. This is why this is a little freaky, okay? Is because if I were to do a position time graph of this parabola, it would look something like this. And then this is 2.78 right here. But see, the thing is, the math didn't know that you are not including negative time. That's something you had to know because, you're a human and you know that time doesn't go backwards. But the math didn't know that. So the math said, well, if I were to continue this parabola backwards in time, all you were asking me was to tell me when this thing equals 0. Right? That's why we have the equals 0 part. So, at negative 1.46 time, it would have also equaled 0. That's all it's saying. Does that make sense? But then we know that physically that's impossible, so we just cross it out and we say, well, this is the answer that is practical. Because in a parabola, you get two answers. We cool with that? So I think that the lesson I really wanted to teach you here was this idea of being able to, having the freedom to call down the positive y direction. That really trips people out. But you're going to find that, here, why don't we solve another one? Do you mind if I erase this? Okay, real quick, just to give you a heads up. The second thing that I want to kind of reinforce with this problem is this is the first problem where we had to use the quadratic equation, but you'll have to use the quadratic equation. As you can see, this is actually a quadratic function as a function of t. So, therefore, the quadratic equation is totally fair game. In the future, if you have something that looks like this, remember the quadratic equation. All right, I'm going to erase this. I'm going to go over a different problem. And then I think I want to go over maybe a little bit of trigonometry, just enough to kind of get you started with it. We cool? All right, let's do another one, and this one will be quick, just to get my point across. What if I did something where I just drop a ball from a certain height? So this is me holding a ball, and I'm dropping it. Pew! From height h. How long will it take? So t equals what? So I'm making this problem up, but I mean, say I drop a ball from a certain height. How long will it take? T equals what? Acceleration is equal to g in the down direction. And I don't have any initial velocity. I just drop it from rest. So v naught is equal to 0. Okay, let's list out our 5 things. V naught equals 0. Acceleration equals g. H is equal to h. And t equals what? Does that make sense? Well, actually, I'm sorry. I screwed up. And I screwed up on purpose. We need to first define a coordinate system. And a lot of you wanted to stick with up being the positive y direction. And I'll say, all right, fine, let's do that. That means a isn't equal to g. A is equal to negative g. And h isn't equal to h. Your delta y, which is the same as h, is actually negative h. Does that make sense? Because you're calling up positive, your change in your y direction is down. Also, you're calling up positive, so gravity is acting down in the opposite direction of gravity. All right, let's plug in the equation. This one's pretty easy. It's delta y equals v naught t plus 1/2 at squared. See, I told you you'd be sick of this equation. All right, and then let's see. V naught is equal to 0. Delta y is negative h equals negative 1/2 gt squared. We cool? Did I freak you out? All I did was I replaced the delta y and the a instead of it. Cool? All right. I have to go through one step where I have to maybe say multiply both sides by negative 1, and I end up getting h is equal to 1/2 gt squared. Can you see that, or is the glare in the way? I can't really do much about the glare, so you're going to have to deal with it. All right. And then to solve for t, I would multiply both sides by 2, getting rid of that. I would divide both sides by g, getting rid of this. And I'd take the square root of both sides. So t is equal to plus or minus the square root of 2h over g. Are we cool? Okay, let's redo this problem, and I'm going to redo it real quick, but this time I'm going to call down positive. That means my velocity initial will still be 0, my acceleration will be positive g, my delta y will be positive h, and my time I'm still looking for. No surprise to you, we're using the same equation, delta y equals v naught t plus 1/2 at squared. The v naught is 0, so I can just cross out that whole thing in the middle, because 0 times t is still 0. This would be positive h equals 1/2 gt squared. Hey, look at this. That's the same thing. So I didn't have to go through that extra step of canceling out both negatives. Because when you cancel out both sides being negatives, you have positive h equals positive 1/2 gt squared. Well, over here, they already told me there. I already got there. And I didn't have to worry about negative g and negative h and all of that kind of stuff. You see how the math corrected itself in the end. Basically, here's the idea, is if you called up positive, you would have two negatives that cancel each other out and make a positive. Whereas if you called down positive, you would just start off with only positives. Does that make sense? It's a subtle thing, and it's not really that big of a deal now, but it will be later. And what I'm going to end up doing is I'm going to end up solving problems quickly and just calling down positive and noting that on the board. And if you guys don't watch this lecture or understand what I'm doing here, then you'll probably be confused with what's coming up or what I'm doing. From there, the problem solving is nothing any different. It's exactly the same steps I would take, so I'm not even going to finish it. But essentially, I want you to get across this idea of down being positive as a possibility of making our lives easier. Does that make sense? All right, cool. Let me cover this real quick, and I'm just going to give you the theory behind it. And then on Wednesday, we'll get heavy into this. Sound good? All right. So I introduced to you the idea between vectors and scalars. A vector is like the displacement. It needs both a magnitude and a direction. I am vector, committing crimes with both magnitude and direction. Oh yeah. Yeah, I don't know if you remember from Despicable Me, but the dude's name was Vector, and he committed crimes with magnitude and direction. Whereas distance would be just straight up magnitude, but no direction. Got it? Now, one of the things we do a lot in math and in physics, especially in physics, is we like to do things where we have a vector and we have, maybe I should draw it a little bit further on the side. We have a vector, okay? Let me actually just motivate this right off the bat. We want to get to solving these types of problems. I shoot a basketball, here's me, and I shoot a basketball at an angle. Angle theta. Because I don't throw things I don't only drop things. I don't only roll things across the floor. I do interesting things, like throw things at angles. Does that make sense? So there's this whole world of physics where we're going from one dimension to motion in two dimensions that we would like to explore. But the problem is we only have those equations that work for one dimension, only the x or only the y. Actually, only the x or only the y. But there's interesting problems out there, like I throw a basketball, where does the basketball go? Or do I even make the basket? Or that kind of stuff. You get it? So what we do in physics, and I'm giving you the secret ahead, right off the bat, is we don't deal with the two dimensions. When we want to solve a two-dimensional motion problem, we don't deal with the two dimensions at the same time. We do something clever. What we do is we say, all right, well, imagine, actually, I don't know why I erased that. It's a basketball hoop. Imagine you're a bird and you're looking down on the situation. You're hovering over the basketball player. The basketball player is throwing the ball like that. Can you envision this? Do you understand what's going on? All right. What you're going to see is, imagine that you're not looking at the basketball, but what you're looking at is the shadow that is on the floor because the basketball is up here and the sun's way up here. So you're watching the shadow as it goes across the floor. Are we cool? That is not two-dimensional motion. That's one-dimensional motion. You see that? And then what you do is you're the bird and you land and say that you're the bird over here. This is a bird with its wings. And you're watching this thing. And there's a wall back here. And there's a big spotlight behind you. And you're watching the shadow as it goes on the wall of the ball moving. So the ball moves like this and the shadow goes up and down. Do you see that? Can you envision this? Can you envision maybe two birds, not the same bird, but two birds? One hovering 1,000 feet directly over, looking at this basketball going in the hoop, and the other going right behind the person or on the side of the person with a shadow on the wall, looking at how this motion works. And the bird up high sees this motion over here, whereas the bird on the side sees this motion over here. And when you combine those two motions, you get two-dimensional motions. When you combine these two one-dimensional pictures, or maybe two one-dimensional movies, you end up getting a two-dimensional motion. Does that make sense to you? So what we're going to do, and this is the clever thing that we're going to do, is we're going to take a two-dimensional vector and break it up into what I call its components. There's an x component and a y component. Let's say that this is v, then this would be vx and vy. What I'm doing is I'm taking something that is moving in two dimensions, and I'm saying, well, what is that equivalent to in moving in just the x direction and the y direction? It's almost like Pac-Man. All right. Say that there was like a Pac-Man mission. Where have you ever played Pac-Man? The Pac-Man has four directions it can move. It can move up, down, left, and right. Up, down, left, and right. That's it. It can only move up, down, left, and right. Say Pac-Man has to go from here to here. In fact, if Pac-Man had to go from here to here, that would actually constitute a displacement because you're saying a starting point, an ending point, and you're giving it a direction, an angle at which he has to travel. Does that make sense? But the problem is that Pac-Man can't move at a diagonal. Pac-Man can only move up, down, or right, left. So what we have to do is we have to take this two-dimensional instructions that has a magnitude and direction and turn it into two one-dimensional instructions. We have to tell the Pac-Man to go a certain distance to the right and a certain distance up. We have to say, I want you to go, if this is my displacement d, then I want you to go d sub x and d sub y. Does that make sense? Because if you go these smaller distances, dx and dy, you'll get to the same spot, Pac-Man, don't worry. You'll look like you went this way, but you didn't. You actually only went this way and this way. So what we're going to be doing is we're going to break two-dimensional things into one-dimensional. Either x or y. That's it. Because one-dimensional deals with only x or only y. Two-dimensional deals with both x and y. But I can take all the information from the two-dimensional and encode it into two separate one-dimensional things. I know. This is a brain buster. I don't know if I'm making this harder than it actually is. Anyway, to do this, we're going to have to rely on three special functions from trigonometry. Have you taken trigonometry? No. Okay. Have you heard of sine, cosine, and tangent? Have you seen those before? In geometry? Good, good. Well, we're going to be using the stuff that you learned in geometry. Now, you know, of course, I don't ever write sine with S-I-N-E, even though technically that's how to spell it. You always abbreviate S-I-N. Cosine is always abbreviated C-O-S, and tangent is always T-A-N, right? And so I'm assuming you've heard of SOHCAHTOA. Have you heard of SOHCAHTOA before? If you haven't, just say no. I'm fine with it either way. Okay. All right. Well, I'll go through SOHCAHTOA real quickly with you. Basically, we see this side of the triangle as the hypotenuse. We see this side of the triangle as the opposite. And this one is the adjacent. All right, I have a question for you. I know why the hypotenuse is the hypotenuse, because it's the longest side in the triangle. This is, of course, a right triangle. And SOHCAHTOA only works with right triangles. I understand why the hypotenuse is called the hypotenuse and which side it is. I can identify it right off the bat. But why is this side the opposite and this side the adjacent? Why isn't it that this one's the adjacent and that's the opposite? Do you know? Okay. Well, it actually could be switched. It totally could be. The way you tell which is which is you look at the angle. Adjacent means right next to. So if someone's standing adjacent to you, they're standing right next to you on your left or right. They're touching shoulders with you. But if someone is standing opposite from you, maybe you're standing in a big circle, they're standing on the other side of the room. So if you look at the angle over here, this side is opposite of that angle, theta. That's why we call it the opposite side. And if you look at this side right here, it's next to this angle, theta. Does that make sense? Yes, so if you were standing at that angle, the opposite side would be this length, whereas the adjacent side would be this length. Now, be careful, because sometimes I don't always call that the right angle. I call this the angle, maybe. Let's say that's theta. Well, then this would be the opposite, and this would be the adjacent. It would switch. Does that make sense? So the hypotenuse is the one that's always across from the right angle. It's always the biggest length. But the opposite and adjacent sides, those change depending on where your angle that you're referencing is. Does that make sense? All right. Now, the mnemonic device SOHCAHTOA is basically telling you three equations. It's saying that sine of theta is equal to opposite over hypotenuse. So, the next part is cosine of theta is equal to adjacent over hypotenuse. And tangent of theta is opposite over adjacent. You've seen this before? Yes or no? Okay, good. So, with that problem where I said, hey, Pac-Man, you need to go a distance d at an angle theta, and what I wanted to find out was what is dx and what is dy, then what I would be able to tell Pac-Man is I said, all right, fine. If I were to take the sine of theta, that's equal to dy divided by d. You see what I did there? This is applying to this second triangle right here, the one on the bottom. Okay? And then you wanted to find out what is dy? Well, dy is equal to d sine theta. All I did was I multiplied d to both sides. Took that d from under there and put it on the top. Does that make sense? So if d were 10 and theta were like 30 degrees, I would punch into my calculator 10 times sine of 30 degrees. And whatever number that is, that's my dy. That's how far up arrow Pac-Man has to push in order to get from here to here. I want to solve for dx, so the way I would do that is I would say, okay, well, dx involves the adjacent and the hypotenuse. Is there an equation in SOHCAHTOA that deals with adjacent and hypotenuse? Cosine, very good, exactly. So I would say cosine of theta is equal to dx over d, because dx is my adjacent side. And in order to get dx, I would simply say that dx is equal to d cosine theta. I just multiplied d on both sides. Does that make sense? So I would tell Pac-Man, hey, you need to press the right arrow. I would calculate out what d cosine theta is. Try it for me. Do you have a calculator on you? Or if you don't have a calculator, just let me know. Okay, try type in 10 times the cosine of 30. What do you get? Do you... That can't be right. I bet you it's because you have your calculator in radians and it's not in degrees. Do you know how to switch that? Oh, okay. Well, bring in your phone and I'll show you how to switch it. But anyway, what you would do is you would plug in d times the cosine of 30 degrees, with your phone being in degrees. and you would plug in d times the sine of 30 degrees, and you would say, well, Mr. Pac-Man, you would have to travel this far to the right and this far up in order to be equivalent to that two-dimensional motion you wanted to try to accomplish. Does that make sense? And this is the big thing. This is the crazy thing that messes everyone up. And I think that the reason why it messes people up is because I think it's the teacher's fault. I think that teachers don't take the time to explain this part to you. They just assume that you remember it from geometry. But I'm willing to bet that when you learned this in geometry, you didn't know what the heck you were learning this for. Am I right? So you learned it, you learned it enough so you can pass a test, but you didn't really get it, like the power of it. And so you forgot it. Or you just like, it's not important. I don't think I'll ever use it again. And then what physics teachers do is we just kind of go, and remember SOHCAHTOA, blah, 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 blah. We just burn right through it. And it burns students every single time. Because they didn't spend the time, hey, remember SOHCAHTOA? I used to do that a lot. And that's why this semester I'm deciding I'm going to spend a whole chapter on SOHCAHTOA. We're going to spend chapter 3 is all about SOHCAHTOA. And once we get that mastered, we'll move on to chapter 4. Which is all about two-dimensional motion, which is all about applying SOHCAHTOA. But if you can get SOHCAHTOA and learn it good, because if you can learn this good, you'll be set for the rest of the quarter. The rest of the quarter will not be tough for you. If you can understand this and one-dimensional motion. Because I already gave you the big secret, that two-dimensional motion is really just one-dimensional motion broken into two parts. You can kind of see what's going on here, right? Two-dimensional motion looks like this, but now we can use trigonometry to break that two-dimensional motion into a horizontal part and a vertical part. Which is why I've been interchanging this delta x with a delta y. Because I'm saying, well, I'm applying it to the x direction, or, well, I'm applying it to the y direction. And notice how I usually am very careful with saying delta x equals v naught t plus 1/2 a x t squared. Whereas delta y equals v naught t plus 1/2 a y t squared. Because I'm considering the two different directions that we're getting at. That's why I put a little x over here and a little y over there, to remind me that, hey, I'm talking about acceleration in the y direction for this equation, whereas in the x direction for that equation. That's the big secret, my friend. If you can master that, I think you'll be sitting pretty well with physics. Anyway, I'm way over my time. I had fun. I'll see you folks next Wednesday, or this coming Wednesday, and we'll probably just do this all day long. Any questions? I'm disappointed to see where everybody else is, but I don't know. Who knows? Yeah, it's just a virtual class on Wednesday. We're not doing any lab. All right. I'll see you later.